Saturn, the jewel of our solar system. A planet so beautiful, it looks unreal. Those massive rings. That golden glow. That perfect symmetry. But here's the problem. According to physics, Saturn shouldn't exist. At least, not in the way we see it today. Its rings should have disappeared. Its core formation shouldn't have worked the way we thought. Its storms defy expectations. And its very structure challenges traditional planet formation models. So what is Saturn really? A cosmic accident? A failed star? Or evidence that our models of planetary physics are incomplete? Let's break it down. Saturn's rings are its most iconic feature. But here's the issue. Those rings are fragile. They're made mostly of ice particles, ranging from tiny grains to house-sized chunks. Over time, gravitational interactions, radiation pressure, and micrometeorite bombardment should darken and disperse them. Physics predicts that bright icy rings shouldn't last billions of years. Yet Saturn is about 4.5 billion years old. So why are the rings still so bright and clean? Data from the Cassini, Huygens mission suggests the rings might be only 100 to 400 million years old. That's extremely young in cosmic terms. Which raises a wild possibility. Are we living in a rare moment of cosmic timing, where Saturn just happens to have recently formed its rings? Or are our calculations about ring stability incomplete? If the rings are temporary, then Saturn without rings is the real, normal. And we are witnessing a short-lived phase that alone challenges assumptions about planetary permanence. Traditional planet formation theory says gas giants form like this. A solid rocky core forms first. It grows massive enough to gravitationally pull in hydrogen and helium. It becomes a gas giant. Simple, right? Except Saturn complicates this. Recent gravitational data from Cassini suggests Saturn's core is not solid. It may be fuzzy, a diffuse mixture of rock, ice, and metallic hydrogen blending into the surrounding layers. Instead of a clean, solid center, Saturn might have a diluted core extending thousands of kilometers. That doesn't fully match classical core accretion models. It suggests either Saturn formed differently than we thought, or giant impacts early in its history mixed everything together, or our planet formation models need revision. In other words, Saturn might be rewriting planetary physics textbooks. At Saturn's North Pole, there is a perfect hexagon. Not metaphorically. A literal six-sided jet stream. This massive structure has persisted for decades. Fluid dynamics tells us that turbulence should create chaos, not geometric perfection. Yet Saturn maintains this stable polygonal storm. Scientists can reproduce hexagonal flows in lab simulations using rotating fluids. But seeing it naturally at planetary scale? That's extraordinary. It suggests that under certain rotational speeds and atmospheric conditions, nature prefers geometry. Saturn rotates incredibly fast, about 10.7 hours per day. That rapid rotation may stabilize these jet streams into geometric shapes. But here's the deeper question. If such structures are possible, how many other, impossible, atmospheric phenomena are we missing across the universe? Saturn is the least dense planet in the solar system. Its average density is lower than water. If you had a bathtub big enough, Saturn would float. That seems absurd. How can something 95 times more massive than Earth be less dense than water? The answer lies in its composition. Mostly hydrogen and helium. Enormous volume. Relatively small heavy element core. But this low density creates another issue. Gas giants close to their stars, exoplanets we've found, often have similar low densities. Some are even more extreme. Saturn might not be unusual. It might be the blueprint. And that changes how we understand planetary diversity across galaxies. Saturn is massive, but not massive enough. To become a star, an object needs enough mass to ignite nuclear fusion. Saturn has about 0.3% of the Sun's mass. That's far below the threshold for hydrogen fusion. However, early in solar system history, if Saturn had accreted just a bit more mass, could it have become a brown dwarf? Probably not, but the idea highlights something important. Planet formation is a delicate balance. Too little mass? Rocky world. More mass? Gas giant. Even more? Brown dwarf. A bit more still? Star. Saturn sits right on the edge of giant planet physics. It represents a boundary object. So does Saturn truly not exist, according to physics? Not exactly, but it pushes physics to its limits. It exposes weaknesses in ring longevity models, core formation theories, atmospheric dynamics predictions, planetary evolution timelines. And that's the beauty of science. When something doesn't fit perfectly, it forces us to improve our understanding. Saturn is not a mistake. It's a clue. A reminder that nature is more creative than our equations. Saturn's rings aren't stable. They're dying. Data from the Cassini, Huygens revealed something shocking. The rings are slowly raining down into Saturn. This phenomenon is called ring rain. Charged ice particles spiral inward along magnetic field lines, falling into the atmosphere. At the current rate, Saturn could lose its rings in about 100 million years. Cosmically speaking, that's tomorrow. If rings are temporary and unstable, then Saturn as we know it is in a fleeting phase. We're witnessing a planetary transition. The version of Saturn we admire might be a brief accident of timing. Most planets have tilted magnetic fields. Earth's magnetic axis is offset. Jupiter's is clearly tilted. But Saturn? Its magnetic field is almost perfectly aligned with its rotational axis. That shouldn't happen. According to dynamo theory, magnetic fields are generated by internal fluid motion, and that motion usually creates a symmetry. Yet Saturn's field is strangely symmetric. Too symmetric. This creates a problem. Scientists can't accurately measure Saturn's rotation rate using magnetic wobble, because there isn't one. It suggests either our dynamo models are incomplete, or Saturn's interior behaves differently than any other planet we've studied. In planetary physics, symmetry can be more suspicious than chaos.